Welcome back everybody to my channel. In this video we want to practice a tree traverse using Python for problem 199 binary tree right side view on LeetCode. So in this problem we are given a root of a binary tree. Each node in this tree is of type tree node, and each of them has a value of type integer and a left and right pointer pointing to another object of type tree node, like the one that you can see here in this example. And we want to find the right sub view of this binary tree. And what does that mean? So for this specific tree given in this example here, imagine yourself, you're observing the tree from here. So you're observing the nodes, and the only nodes that we can see are nodes 1, 3, and 4 because we cannot see node 2 and 5 because these three are blocking them. So we should return a list of integers of all nodes we can see if we stand on the right side of this binary tree. So the first thing comes to mind for this specific tree is starting from node or starting from root. If we always go to the right, we can quickly find this by just traversing the depths of this tree by only visiting 3 nodes and returning them quickly. But this is not the thing that we can do every time, because if I adjust this tree by adding 2 new nodes like the 6 and 7, by only traversing to the right we cannot find 7, because 7 should also be returned if we are observing the tree from the right, because there is no node here blocking the node 7, and 7 should be included as well. So what we can do here, while we are traversing the tree, we know the depths of each node. So considering the root itself at depth 0, anything for its children, all of these children are depths 1, and then the next layer depths 2, and etc. So we know if we observe the tree for every depth, we can only see at maximum of 1 node, and the only node that we can see is the rightmost node in that depth. So in the example that I adjusted for layer 3 or for depth 3, the only node that we could see was node 7 because there is nothing else could block it. So the only thing that we want to find out is a list of all rightmost nodes for each depth separately. And while we're traversing the tree, if we always start from left, or it is called in order traverse, so whenever we are visiting a node, we make sure that we first go to the left node, visit all its dependents, and then in a recursive function, then we go to the right. So starting from the left, for each depth, for the root, it is already 1. But when we visit a node 2, so this is the first node that we are visiting at depth 1. So we add it here. So this is 2. And then we are just visiting all of its dependents recursively, doing the same thing. And then while we are coming back from the recursion and then visiting 3 for depth 1, so we replace 2 by a 3 as the rightmost node for that specific depth. And at the end, we can just return all of these nodes for each depth as the rightmost node for all of them. So what we need here, let me start the implementation. So we need for initializing this class. So for each steps, we want to keep track of the rightmost node. So in order to find each steps quickly, I want to define the dictionary. So self that rightmost equals a dictionary. The key is the depth, and then we can quickly just replace the new node with if there's anything present from the previous iterations, or just initializing as the rightmost node for each time we visited depths. So I want to define another function that build that traverse, or so let me call it traverse, starting from the root. And as we discussed, while we are traversing a tree, we should know the depths of the current node that we are visiting. So I want to start define it by depths, and then initially for the root, as we discussed, we call it and initialize it with 0. So root is always at depth 0, and whenever we are visiting children, we can simply increase that depth by 1. And as always, whenever we are implementing a recursive function, we should always consider the edge cases or the halt cases that we should jump back or stop the recursion. So if the root is none, for example, in this case, okay, we should simply return, break the recursion. Otherwise, we know the depths and we can update the self.rightmost of depth equal root.value. So for the current depth that we are at, we can simply update the node, update the rightmost node of that depth with the value of the current node that we are visiting. And after that, as we discussed, we should make sure that we are always visiting left children first and then go to the right children. So self.traverse root.left and then depth plus 1. Similarly for the right children and depth plus 1. And then in the solution, you can simply call self.traverse of root. We don't need to pass depths because initially by default it is 0. So after that, we know we have a dictionary that in that dictionary we have some depths. For 0 is pointing to 1. The key depth 1 is pointing to node 3 as the rightmost node, and depth 2 is pointing to 4. So what we simply need to return is a list of iterate through all of these key values and then create a list out of that and return it. One way is we can have access to the self.rightmost keys. So these are all keys and we can sort them and then return them. But while we are traversing, we can initialize self.maxDepth equal to 0. And whenever we are visiting a node, we can simply update the self.maxDepth equal to the maximum of itself and the current depth that we're visiting. And when we are building the solution for this problem, we know that if we start from 0 and then iterate all the way to self.maximum depths, we are visiting the nodes in order, starting from the smallest and to the last node in the maximum depths that we have visited in this tree traversal. So we can return what we are iterating through is for depths in range self.maxDepths plus 1, because for one node we are just assigning to the max, but ranges in Python are not inclusive. So we are returning a list and the rightmost of that depth. And this is the list that we are creating all integers, returning as a solution. So let me try to debug that. Okay, it is a dictionary, so it should be D. Okay, so let me submit that. D is not defined. Oh, if it is an empty. So, and the problem, it says the root could be empty. So we can simply say if root is none, return an empty list. This is an edge case that we didn't consider initially. If I submit that again, so here we go. So in terms of time complexity, we are visiting all nodes in this tree. So the time complexity is O(n) because we are visiting each tree at least only once. But in terms of memory complexity, we are allocating an extra memory of size the depths of that tree, because for each depth we are only keep tracking of only one node. And if the tree is balanced, so the memory complexity is the O of log m. Otherwise, if the tree is not balanced necessarily, so it is the in the order of the maximum depth of that tree, the extra memory that we are using in this solution. Okay, so that was everything for this problem. Hope you enjoyed it.